Hey guys, today we're going to talk about atoms. And you've learned about atoms since you were, well, before you were in third grade. You know that there's a nucleus, and in that nucleus there are protons and neutrons, and there's electrons that are whizzing around outside that nucleus. And you know that an atom is the tiniest particle that you can have of an element, and if you have a tinier particle, then you don't have an atom anymore. You have the parts, the protons, electrons, and neutrons. And you've seen this model, the Bohr model, where there's a first energy level, a second energy level, a third energy level, and on those energy levels you draw electrons, right? Okay? And deep in the middle is the nucleus. So you know that, you've seen that. You can picture this as an atom, where right here is the nucleus, and in that nucleus you have protons and neutrons. And way outside out here, and these are depicted in different colors, are electrons. So protons and neutrons are in the nucleus and electrons are outside. Electrons are charged negative. Protons are charged positive. And neutrons are charged nothing because they're neutral. If you look, this is a handy way to remember the parts of an atom. You write with a pen or a pencil, and the first three letters are the parts of an atom: proton, electron, and neutron. Now if you look, this is a Bohr model, as is this. It's just more three-dimensional, but it's just that, it's a model. And so if you look, there's a history of these models, a history of what we've thought about the atom. And there's a gentleman named Democritus, and he lived back in 460 BC. That's a long time ago. Back in the time of Aristotle, all those guys. And they thought that there were four elements: fire, earth, air, and wind, or water, excuse me. Earth, wind, fire, and water. So he said, I think there's these tiny things. They're called atomos. It's indivisible. In other words, that tree, that rock, that stream, that water, the air, dirt, you can break it down into tiny particles, and after that, there's nothing. So he came up with the word, he coined that word atom, atomos, indivisible. Dalton, look at the difference in time, 460 BC to 1803 AD. Lots of stuff happened in between there. Dalton pretty much came up with the same thing. He says, and his is called the billiard ball model, that you have really these things that are indivisible. It's just like a blob. That atom is indivisible. He didn't have protons, electrons, or neutrons. Nothing. He said that an element, an atom of one element, like an atom of oxygen, is the same as any other atom of oxygen. And an atom of oxygen is not the same as an atom of carbon or fluorine or argon. So he knew there were atoms, he knew there were different kinds of elements, and he did a lot of experiments and based things on experiments and came up with relationships of how our compounds are related to each other, like H2O and NaCl. He did a lot of things with ratios. We'll come back to that later. Now there's this guy now called Thomson, and his name is J.J. Thomson. And J.J. Thomson has the plum pudding model. And I'm going to call him J.J. P.P. Thomson, not to be disrespectful, but his model is the plum pudding model. So J.J. P.P. Thomson comes up with this model that says, I've got all this positive pudding, this positive stuff, and in it is stuck these plums, or these electrons, that are just kind of in there, like a Jell-O salad. They're just floating around. And that's what he thought in 1897. That's not that long ago. That's Civil War time. So matter was thought of as this positive pudding with negative particles floating around in it. He did some experiments, and we'll go into that later. I'll do a podcast just on history of the atom. But he was wrong. And through some experimentation, back in 1912, turn of the century, last century, and look at Bohr, close behind, who's a student of Rutherford's. Rutherford said, you know what? This is what the atom looks like. You've got this atom. It's got a nucleus in the center. Okay? His nickname is Gold Foil Man because he used gold foil to determine this. And he bombarded some particles through and found out that the nucleus was positive, super duper dense in the center. But he still thought that these electrons were just randomly, looks like a face, were randomly floating around, just willy-nilly flying around like a bunch of flies in a room. Bohr said, that's impossible. If these electrons are flying around, eventually they're going to lose energy, and this positive nucleus is going to attract all these negative electrons as they lose energy, and poof, matter would disappear. It would implode. Impossible. So Bohr says, what you know, we're going to put our electrons in energy levels. He calls them orbits. You can really see that, can you? Not at all. These are orbits, like the planets. So sometimes we call his model the planetary model. Now that's not true either. After 1930, we've been doing all kinds of experiments past that. It's called the quantum cloud model, or the charge cloud model. There's a bunch of guys. Einstein, Heisenberg, Schrodinger, a bunch of people are involved in this model. So if you look, this is Bohr's model, and this is a three-dimensional version of what you know as this bullseye. Okay, and this is a charged cloud model. Here's my nucleus with my protons and my neutrons. My electrons are like traveling all over. They're just randomly going all over the place. So the places where the electrons found are called orbits in Bohr's model. And in the current model, remember we call it the charged cloud model, or the quantum mechanical model. All these are in orbitals. This model has a set path, where these are running around a path and they stay on that path, right? Electrons on that path stay on that path. Electrons on this path stay on this path, and they don't overlap. Kind of like Mercury, and then the next planet, Venus, and then the Earth. They all have orbits. In this model, the current model, these electrons are going all over the place. There's no set path. They're going randomly all over. They're not overlapping though. So this is a set area. And we'll go into that later as well. So an orbital is a set area. It's the current model. An orbit is Bohr's. It's a set path. It's in the planetary model. So Bohr's model is not completely wrong. It's a good way to picture it, but the correct version is orbital. And I'll do a hotel. That's the 1s2, 2s2 stuff. So in an atom, okay, and let's picture it with Bohr's model here. You have to picture that there's three particles. There's the proton, the neutron, and the electron. Protons are positive one. Electrons are negative one. But what's weird is protons and neutrons are the same size, and electrons are super duper tiny. Now this isn't to scale, so it doesn't give you an idea. Matter of fact, I make the proton big and the neutron big, and they're both the same size. Okay, and electrons are actually tiny. So if you look at this over here, this is a real nice idea, so you can, or picture, so you can get an idea. Protons and neutrons weigh the same. Protons and electrons do not. Look at this. For every one proton, you need 1,830 electrons to equal one proton. They're tiny. So I'm going to give an electron a name. It's like an earring. It's tiny. Protons and neutrons are like a medicine ball that you play with in PE. They're huge. They do not have the same charge. They are not even charged. Neutrons aren't charged. Protons are charged. They're the same mass. Protons and electrons are way different, but they are equal in charge but opposite from each other. So in other words, protons and neutrons weigh the same. Electrons are tiny compared to protons and neutrons. Neutrons are neutral, and protons are +1 and electrons are -1. And I find that weird, that this tiny electron that actually should probably look about that big is -1. It's equal to the +1 proton, even though it's tinier. Funny. So protons and neutrons, it turns out, and this is extra credit, they're actually composed of smaller particles, and these particles are called quarks. There's your definition. Okay? They're teeny, teeny particles. It turns out that they have different names. How about this? Up, charm, top, down, strange, and bottom. How about that? And look at these fine little characters. If you notice, they have fractions. Some are positive, some are negative. It turns out there's way deeper stuff going on than what we're talking about in this class. There's quarks and gluons and leptons and hadrons and lots more. You're interested, come see me. But it turns out that electrons are something called a lepton, and protons and neutrons are actually composed of quarks. So if you look, a proton is composed of an up quark, another up quark, see this right here, and a down quark. And if you look at their fractions, the overall charge balance, is positive. And the way neutrons are composed, they are composed of 2/3 positive, which is an up. Do you see that? And there are 2 downs, and those downs are -1/3 and -1/3. So these cancel out, and they're neutral. How about that? So if you're interested, you can come see me about this, and I'll tell you a little bit more. So now let's actually go into what an atom is, an ion, and an isotope. An atom is just what we've been talking about. It's a particle where the protons and the neutrons are equal. Not the neutrons. The electrons are equal to each other. It's neutral. It has no charge. So all the positives are equal to all the negatives. I'm not going to use that color. Let's use this color, maybe. No, that's too close. So we'll use baby blue. There you go. I don't know. All right, what's an ion? An ion is a charged particle. We learned about that before. And it's either charged positive or negative. And if that's true, that means the protons, I'll put this here, protons equal electrons. Protons do not equal electrons in this case. Now, the thing about an atom is the protons are like the ID card. They're like the DNA. If I have DNA, my DNA is different than yours. Protons never change. And if they do, you have a different element. So protons are going to stay the same. So an ion specifically is when electrons go up or electrons go down. If I have a certain amount of protons and my electrons are greater, I'm going to have a negative ion. If I have less electrons, I'm going to have a positive ion. And we'll go into this in a chart, okay? An isotope, protons and electrons we're not really talking about, okay? Protons could be equal to electrons, or protons don't have to be equal to electrons. We're not talking about electrons. We're talking in an isotope, the number of neutrons can go up, or the number of neutrons can go down. So an ion is electrons changing. It's charged. My way of remembering that is if I'm a policeman and I'm pulling you over, I'm going to keep my eye on you. I keep my eye on you because I could charge you with a ticket. So I'm going to be charged positive or negative. An isotope, I'm changing my mass. My weight is changing. So my neutrons are going up or down. Let's practice. First of all, I need to look at the periodic table. If you look right here, on the periodic table, every single one of these boxes has a name, a number, a symbol, and a weight. So let's look at nitrogen. Nitrogen, I'm going to write like this with its symbol. The atomic number is the number of protons. The symbol is a symbol, and the name is the name of it. The atomic weight, actually we don't call it atomic weight anymore, we call it atomic mass. And this actually should say 14.01. Alright? Now the old term for mass, old school stuff, is AMU, atomic mass unit. We now call it grams. But the atomic mass, weight, we can't really use weight. Weight's based on gravity, so we use mass. Atomic mass is in grams. And the atomic mass is the protons and the neutrons added together, and also the electrons. The electrons are tiny, though. Remember we said they don't weigh anything. So let's go back to these vocabulary words. Atomic number is the number of protons. It doesn't change. If it does change, then, like, here's nitrogen, 7. That's the atomic number. If I had 9, I'd have fluorine. If I have, 13, I have aluminum. So that atomic number tells me who I am. It's the ID card of the atom, of the element. Protons in an atom are equal to the number of electrons, because positive equals negative if I'm an atom. So I'm going to go ahead and take the atomic number and I'm going to write it down here. That's where I write the atomic number. That's where it lives. Now the atomic mass I'm going to round. And I'm going to round that number to a whole number, and 14.01 rounds to 14. This is called the mass number. And I had the hardest time with this when I first learned this, because I didn't have a good explanation in high school from my teacher. The atomic mass is the mass that's on the periodic table. All these are atomic masses. Okay, not atomic weight, but atomic mass. So every single thing in this box, and actually what they've done, they've rounded this. If you look at any periodic table, lithium's mass is going to be 6.941. Okay, so you take that, if that was in lithium's box on another periodic table, you have to round it. So I would actually have to take this 14.01 grams and round it to 14. That is it's just a number. It's not a decimal. It's just a number. And that mass number is what I put up here. So I'm going to take that 14 and that 7 in nitrogen and I subtract it. And when I subtract it, I get the neutrons. So 14 minus 7 is 7. I get 7 neutrons. This is protons plus neutrons. Remember, because electrons are tiny. This is protons. And if I subtract, I get the number of neutrons. This is an atom, so I don't write any kind of charge up here at all. Nothing. I don't write a 0. There's no charge. Okay, later on we'll see a plus or a minus. And this is how I write the symbol to figure out how to figure out the protons, electrons, and neutrons in nitrogen. So let's review. And again, I pulled a bad periodic table. Sorry. This in lithium's box is 6.941 on any other periodic table. In beryllium's box, it's 9.01. This is 1.01. So this periodic table, they've already rounded it. This is 24.3 something in another periodic table. Okay, 0.305. So the atomic mass, let's take beryllium. The atomic mass for beryllium is 9.01. We could call it AMUs. In our world now we call it grams. The mass number is that number, that atomic mass, and we're going to take it and we're going to round it. So that would be 9. And I would take that number and put it right here, because that's what you want. You want a number. The atomic number for beryllium is 4. The atomic number tells me the number of protons. So I'm going to take that number 4 and put it right here. If you forget, the big number in the box gets rounded and it always goes on top, because you are going to subtract these two and you're going to get neutrons. So 9 minus 4 is 5 neutrons. So if I wanted to find out protons, electrons, and neutrons for beryllium, I would have 4 protons, because protons is the same as the atomic number. I would have 4 electrons, because this is for an atom of beryllium. Right? So in an atom, the protons and the electrons are equal to each other. And to get neutrons, I set my element up like this using this format, and I subtract, and the number of neutrons are 5. Let's try another one. Okay, so let's try magnesium, and I just got rid of all the stuff I wrote down. So magnesium was 24.305. Any other periodic table, you would see 24.305 here. So atomic mass is what? 24.305. The mass number is just that number, and it's rounded, 24. The atomic number is 12. The atomic number is the same as the number of protons. This is an atom of magnesium. So we know there's 12 protons because these are the same. We know there's 12 electrons because it's not charged. We know to get neutrons that we're going to subtract. I like writing the word neutrons out because there's a lot of numbers. Things are going on here. I get confused. Okay, these are the same. And neutrons, when you subtract, you get 12. Now it just so happens that some of these ratios are the same in some of these upper elements. They're not always the same though. Okay, so those are atoms. Let's go ahead and do an ion. And let's do sodium. And sodium's mass on any other periodic table is actually 22. I'm going to write it out here. Sorry. Actually, you know what I'll do? I'll write a sodium right here so you can see it. Okay? It will be 22.99 in a box on the periodic table. Okay? And we'll go ahead and do fluorine also. And fluorine on a periodic table would be 18.99, and the atomic number is 9. Okay, but we're not going to do atoms this time. We're going to do ions. So let's find all the protons, electrons, and neutrons for ions. So what's about an ion of sodium? Sodium on the periodic table is in the +1 column. So it's got a charge of +1. So we're going to find out protons, electrons, and neutrons for the sodium +1 ion. What's the atomic mass for sodium? I'm going to write Na right here. I'll write it like this. The atomic mass, actually no, let me write it over here. That way there's room. Okay? So the atomic mass is 22.99 AMUs, or grams in today's world. What's the mass number? The mass number is the atomic mass rounded. So we're going to round it to 23. That rounds to 23, doesn't it? That 23, actually let's not use red because we're using red on this. Let's use black. 23 goes right here. That's the big number in sodium's box. What's the atomic number? The atomic number for sodium is the whole number. There are 11 protons. So I'm going to put 11 here. Okay? So my atomic number is 11. That means my protons are 11. They're equal to each other always, like the DNA. Now, I'm not sure how many electrons there are because I'm talking about a word ion. But I do know how to find neutrons. I'm going to go ahead and subtract. Write the word neutron. Alright? When I write the word neutron here, I subtract and I get 12 neutrons. So 12 neutrons, 11 protons, right? And how many electrons? So I got 12 neutrons over here. How many electrons? Well, normally protons and electrons are equal to each other. But in ion, I either lost or gained an electron. And in this case, sodium is a +1. That means I lost an electron. That means I have one more positive than I do negative. And to help you, you can write protons are positive out here and electrons are negative. If I'm a +1 ion, then this has to be true. Do you see that? I have 11 protons and 10 electrons. You can ask yourself, looking at these two values here, electrons and protons, which one's bigger? The protons are. By how many? 1. What's its charge? +1. That matches that. So you know that that is the correct information for a sodium +1 ion. Let's go ahead and do the same thing for fluorine. But fluorine is on the other side of the periodic table. It's a halogen. So if you look at the periodic table, bad periodic table, fluorine will be right here, and it's in the -1 column. So we're going to find all this information out, protons, electrons, and neutrons, for an ion of fluorine, and an ion of fluorine has a charge of -1. So let's do this. What's the atomic mass for fluorine? You look in its box, and this is the atomic mass. 18.99 AMUs or grams. And let me go ahead and rewrite this a little clearer for you. 18.99. What's the mass number? It's the atomic mass rounded. So it's going to be 19. And that number goes up here. What's the atomic number? 9. Okay, 9. So the atomic number is 9. That tells me the number of protons, doesn't it? So I know protons. I take that number 9 and I write it down here. Bigger number in the box right here gets rounded, goes on the top. Small number or atomic number goes on the bottom. Because what are you going to do with them? You're going to subtract them, right? Let me move this over here. So when I subtract them, I get 10. And I should have already, or I write at the same time when I'm doing this, 10 neutrons. So I have 10 neutrons. By the way, to determine this was a -1 ion already, that was what was given. Find the protons, electrons, and neutrons for a -1 ion. So what's this mean if it's -1? That means the protons and the electrons are not equal to each other. The positives and the negatives are not balanced. It either lost or gained. If it's over here and it's a nonmetal, that means it's a gainer. Over here, the metals, these are losers. These become charged positive, and these become charged negative. Fluorine's -1. That means you have one more negative than you do positives. So therefore, let's see if that makes sense. I'm going to have 10 electrons. Does it make sense? Which number is bigger? Electrons. By how many? 1. And if it's 1 bigger, then it's negative by 1. It's a -1 ion. Ta-da! So electrons, you need to figure out sometimes by doing this process. Neutrons you subtract. All right, I'll do just a couple more. So carbon has a mass of, or a symbol, as element name of carbon. Symbol of C, atomic number 6. That means it has 6 protons. If you look in its box, it's 12/6. And if you subtract, that gives you 6 neutrons. If it's an atom, it has 6 electrons. I know this is fast, but I'm going to just go through real quick so you can see in a chart form. The sodium +1 ion, okay, that would be the symbol. The name would be sodium. The atomic number is 11. Number of protons are 11. Okay, to do the mass, you take 22.99 off the periodic table and round it to 23. Put the 11 here and you subtract. if you subtract, you get 12 neutrons. We know it's a +1 ion, so that means the protons and electrons are not equal, and this has 10 electrons. This is an ion. This is an atom, because the electrons and protons are equal, and here they are not. A fluorine -1 ion has a mass number of 19, 18.99 rounded. The name is fluorine, the fluoride ion. The symbol is F-1. The atomic number is 9, because there's 9 protons. Okay? If I subtract these, I get 10 neutrons. And the number of electrons, there's one more electron, and this is a -1 ion. Now, what's an isotope? An isotope is when the neutrons are different. So let me give you an example of an isotope. We'll do another worksheet on it, okay? But if I had carbon and it had 6 protons and 6 electrons, that makes it an atom, doesn't it? Because the electrons and protons are equal. What if my number of neutrons is different? Like I have 7 neutrons. How would I write that? Carbon, 6, because that's the protons. The atomic number doesn't change. But if you add these two together, you have a mass of 13. It doesn't match what's on the periodic table. That's called an isotope. And isotopes are formed when you have nuclear reactions, and you have a nuclear podcast about that. I'll do another podcast later that goes into isotopes a little bit more. All right? But for right now, this is quick and dirty for your midterm.